Are you a JavaScript developer looking to level up your coding skills? Understanding data structures is like having a Swiss Army knife in your programming toolkit. In this guide, we'll dive into 7 essential data structures that can make your code more efficient, cleaner, and more powerful. From the humble array you already use daily to the sophisticated graph that powers your favorite social media platform, these data structures are the building blocks of modern applications. Whether you're preparing for a technical interview or building complex applications, mastering these structures will give you an edge in solving complex problems with elegant solutions. Get ready to transform your JavaScript code from basic to brilliant, and let's dive in to explore these fundamental data structures that every JavaScript developer should know about, starting with the array. An array is a linear data structure that serves as a collection of items. The items in an array may be related or unrelated. The job of the array is to group these items and store them using a single variable or memory address. The items are usually ordered based on their position in the array. The position of each item in an array is known as the index of that item. This can be used to access the item that occupies that particular index in the array, and no two items can have the same index. We can use the index of an item to update the value at a particular position in an array, and you should know that every programming language has its own implementations of array with methods that greatly simplify the process of retrieving and modifying items in the array. You can also add an item to an array by setting the index of that item to be equal to a particular value. Let's move on from that and let us look at what a linked list is. A linked list is a linear data structure where elements called nodes are linked together through pointers or references. This forms a sequence, and unlike arrays, linked lists use non-contiguous memory, enabling efficient insertions and deletions without reallocation. These pointers or references connect the nodes together, defining the order of the list. Non-contiguous memory refers to a memory allocation pattern where data elements are stored in separate, disconnected memory locations rather than in a continuous sequence. This is a key characteristic of linked lists, allowing them to efficiently insert or delete elements without having to reallocate the entire structure, unlike arrays which use contiguous memory blocks. Each node in a linked list contains a value, which is the data stored in that linked list node, and a pointer, which is a reference to the next node in the sequence. Linked lists can easily grow or shrink in size as needed. This is unlike arrays which have a fixed size. Elements are arranged sequentially in a linked list, which makes it a linear data structure. Linked lists can easily adjust their size, making them suitable for situations where the number of elements is not known in advance. Inserting or deleting elements in the middle of a linked list can be done efficiently, as it only requires adjusting pointers. Although accessing a specific element in a linked list can be slower than in an array, as you may need to traverse the list from beginning. Each node in a linked list always stores a pointer to the next node, which can lead to higher memory usage compared to arrays. We can now break down linked lists to see the type of linked list we have, starting with a singly linked list. A singly linked list is a linear data structure where each element, that is the node in the linked list, contains data and a pointer to only the next node in the sequence. Singly linked lists are unidirectional, meaning you can only traverse the list from the head, which is the first node, to the tail, which is the last node. Each node contains a pointer or reference that points to the next node in the list. Now let's look at a doubly linked list. A doubly linked list is a type of linked list where each node contains a data feed and two pointers, one pointing to the previous node and another pointer which is pointing to the next node in the sequence. This structure allows for bidirectional traversal, meaning you can move both forward and backward through the list. Doubly linked list allows for faster insertions and deletions compared to singly linked lists, especially when dealing with elements in the middle of the list. The ability to traverse backward is useful in various applications, such as implementing undo/redo functionality or navigating through a browser history. Doubly linked lists require more memory per node compared to singly linked list due to the extra previous pointer that points to the previous node in the sequence. Their implementation and maintenance can also be slightly more complex than singly linked list. Let's look at a circular linked list. A circular linked list is a variation of a traditional linked list where the last node in the list always points back to the first node in the list instead of pointing to null. This creates a continuous loop of interconnected nodes. The defining feature is the connection of the last node to the first node. This forms a closed loop. Unlike a linear linked list, there is no null pointer at the end of the list, as the list always cycles back to its beginning. Traversal can be initiated from any node and can continue indefinitely, returning to the starting point. You can also have a circular singly linked list where the last node's next pointer points to the first node, and you can have a circular doubly linked list where the last node's next pointer always points to the first node and the first node's previous pointer is pointing back to the last node, allowing for traversal in both directions. Now let's look at a stack. A stack is a linear data structure that follows the last in first out principle. This means that the last element added to the stack will always be the first one to be removed from the stack. Think of it like a stack of plates where you can only take off the top plate first. The stack is used in many algorithms and applications, including function call management, and you are familiar with this from the core stack in JavaScript. It's also used in undo mechanisms in text editors, browser history in the back button, and expression evaluation. The key operations of a stack are push, which allows you to add an element to the stack, and pop, which returns the top element from that stack. You also have the pick method, which allows you to view the top elements in the stack without removing it. Some key characteristics of the stack data structure are: 1. Elements are added and removed from the same head known as the top of the stack. 2. Elements are arranged in a sequential order. And then 3. A stack can be implemented using an array or a linked list, because at the end of the day, what makes a data structure a stack is the way it behaves. As long as it is following that last in first out principle, it is always considered a stack. Let's look at some basic operations of a stack. We have already established that a stack has a push method that allows us to add a new element to the top of the stack. It has a pop method that returns and removes the top element from that stack. It has a pick method which returns the top element without removing it. We can also implement an isEmpty method that allows us to check if the stack is empty. And finally, we have the size property that returns the number of elements in that stack. Let's look at the queue data structure. A queue is a linear data structure that operates on the principle of first in, first out. This means that the first element added to the queue is always the first one to be removed. It functions similarly to a reward queue, such as a line of people waiting for a service where the person who arrived first is always served first. The elements in a queue are always processed in the order that they were added, and the elements are arranged in a sequential order. We have a linear queue, which is the most basic form where insertion happens at the rear and deletion happens at the front. We have a circular queue, which is a linear queue where the last element is connected to the first element, allowing for more efficient use of memory by reusing empty slots. We have a priority queue where elements are processed based on their assigned priority, not strictly on the first in first out order. Then we have a D queue, which is a double-ended queue, and it allows for insertion and deletion from both the front and rear ends of the queue. Now let's look at a hash table. A hash table, which is also known as a hash map or a dictionary, is a powerful data structure that implements an associative array. This means that it stores data in the form of key value pairs, allowing you to efficiently retrieve a value by providing its corresponding key. Think of it like a real word dictionary. You look up a word, which is the key, to find its definition, which is the value. In a hash table, instead of an alphabetical order, a special function is used to figure out where to store and find data. Here is a breakdown of how a hash map works and its key components. A hash map is comprised of key value pairs where the key is a unique identifier for a piece of data. Keys can be almost anything. Strings like name, numbers, like a product ID, or even more complex objects can serve as a key, while the value is the data associated with a particular P, and it could be a person's name, a phone number, a product, whatever. It could be of any data type too. A hash table always have a hash function, and this is the core of a hash table. A hash function is an algorithm that takes a key as input and converts it into a numerical index, which is a hash value or a hash code. This index tells the hash table where to store the underlying value in an underlying array. Lastly, a hash map has an array which is split into buckets or slots. The hash table uses an internal array, which is often called a bucket or slot, to store the key value pairs. The hash function's output, which is the index, points to a specific position in this array. In the best and average case scenarios, insertion and deletion and search operations can be performed in constant time, regardless of the number of elements in the table, and this is incredibly efficient for large data sets. The efficiency of a hash map scales very well with the size of the data, and last but not the least, the key can be of various data types. A hash map is not all sweet without sour, because there are some disadvantages that comes with using a hash map. Starting with 1, hash tables can sometimes consume more memory than other data structures, especially if there are many empty buckets. There is no inherent order because elements are not stored in a particular order, so retrieving elements in sorted order requires additional processing. When the table becomes too full, which means that it has a high load factor, it often needs to be resized. That is, a larger array is created and all existing elements are rehashed and reinserted, which can be an expensive operation. Now, let's look at a tree data structure. The tree data structure is a fundamental nonlinear data structure that simulates a hierarchical tree structure consisting of nodes connected by edges. Each tree has a root node, and every node except the root has exactly one parent. It models relationships where one element can have multiple children elements, but each child element has exactly only one parent element, except for the topmost node, which is known as the root node. Trees are fundamental in computer science for representing hierarchical relationships. Let's look at the core concepts and some terminologies behind the tree data structure. To understand trees, it is essential to know the common terminologies involved with the data structure. First, we have a node, which is the fundamental unit of a tree. Each node can store data and may have links to other nodes in the tree. Next, we have the root, which is the topmost node in a tree. It has no parents, and every tree data structure has exactly one root node. Next, we have the parent node, which is a node that has one or more child. We have the child node, which is a node that is directly connected to another node when moving away from the roots. We have siblings, which are nodes that share the same parents. We have a leaf or external node, which is a node that has no children, and these are the endpoints of a tree. We have an internal node, which is a node that has at least one child, and finally, we have an edge, which is the link or connection between nodes. There are different types of tree, and we are going to start with a binary tree. A binary tree is a hierarchical data structure in which each node has at most two children, referred to as the left child and the right child. This structure is a specialized form of a tree data structure where the degree of each vertex, this is another name for node, is limited to a maximum of 2. That is to say that each parent can only have 2 child. There are different types of binary trees. We have a full binary tree where each node has 0 or 2 children. We have a complete binary tree where all levels are filled except possibly the last level, and the last level has all nodes as far left as possible. We have a perfect binary tree where all internal nodes have 2 children and all leaf nodes are at the same level. We have a balanced binary tree where the height difference between the left and right subtrees of any node is at most 1. This ensures efficient operations. Examples include an AVL tree and a red-black tree. Now let's look at the binary search tree, which is another implementation of the tree data structure. A binary search tree is a tree-based data structure where each node has a value, and the values are ordered in a specific way to enable highly efficient searching, insertion, and deletion operations. For every node in a binary search tree, all values in its left subtree are less than the value of the node itself. All values in its right subtree are greater than the value of the node itself. And thirdly, both the left and right subtrees must also be a binary search tree. Due to the order structure, searching for a specific value can be done in logarithmic time. Let's look at the heap data structure. A heap is a specialized tree-based data structure that satisfies the heap property. This property dictates that for any given node, the value of the parent node is either greater than or equal to in a max heap, or less than or equal to, which is in a min heap, the value of its children. That can be quite confusing, right? I just had my head spinning around just trying to get that out. Heaps are commonly used to implement priority queues and are also a core component of algorithms like heap sort. A heap is always a complete binary tree. This means that all levels of the trees are always fed, except possibly the last level, and all nodes in the last level are as far left as possible. Let's look at the graph data structure. A graph data structure is a non-linear data structure that represents relationships between objects. It consists of nodes, also called vertices, and edges that connect these nodes together. Graphs are used to model real-world relationships such as social networks and transportation systems. Some key concepts of the graph data structures are the node or vertices, which represent the individual objects or entities within the graph. We have edges, and they represent the relationships or connections. Edges can be directed, showing a one-way relationship, or undirected, showing a two-way relationship. Let's look at a directed graph. A directed graph, also known as a digraph, is a graph where edges have a direction, meaning they point from one vertex to another. Examples are a one-way street where Twitter user A follows Twitter user B, but Twitter user B is not following Twitter user A. We have an undirected graph, and an undirected graph is a data structure that represents a collection of interconnected objects where the connection have no specific direction. This means that if there's an edge between node A and node B, you can traverse from A to B and also back from B to A. An example might include friendships on Facebook, where user A is friends with user B and user B is also friends with user A. We have a weighted graph, which is a graph where the edges have associated numerical values called weights, representing various attributes like distance, cost, or time. These weights are crucial for modeling real-world scenarios where different paths have varying costs or significance. Examples of weighted graphs are navigation systems, where the vertices represent locations and edges represent routes, with weights representing distance, travel time, or traffic conditions. Social networks are also an example of weighted graphs because weights on edges could represent the strength of a connection between users. And last but not the least, we have a cyclic graph. In the context of data structure, this is a graph that consists of at least one cycle. A cycle is a path between the graph that starts and always ends with the same node without reusing any edges. Essentially, it is a closed loop in the graph.